Okay, so we're going to be looking at the volume of a sphere. A sphere is a three-dimensional circular object. And we noticed in class, if you have not watched the water demo, I highly recommend that you watch the water demo. We learned that for a sphere that has the same exact height and the same radius as a cone, it takes two cones to fill up the sphere. We also noticed in comparing that to a cylinder, because it took three cones to fill up the cylinder, the sphere was 2/3 of the cylinder. And so as we look at the formula, and we're trying to figure out the formula of that, it is helpful to start with the volume formula for a cone. The volume formula for a cone is pi r squared h divided by 3. Now, because it takes two cones to fill up the sphere, we're going to multiply the whole thing by 2. And so our volume formula is going to be 2 pi r squared h divided by 3. It really is that simple. But as a mathematician, I don't really like that formula. Yesterday in class, we talked about why we might not like that formula. And this letter right here, that's bugging me. Let me show you why that's bugging me. If I go back to the previous slide, we don't usually call the height of a sphere the height, because if I slide this over here and I make this height go straight through the center of a sphere, because a sphere is circular in nature, we don't call it the height, we call it the diameter. Diameter is the distance from one part, one edge of the sphere through the center to another edge of the sphere. And that's called the diameter. And so I'm not going to call it height, I'm going to call it diameter. So I'm going to start by changing this h to a d. Okay, that looks good, right? We're going to have 2 pi r squared d over 3. That looks good, right? Well, we noticed in class that that kind of bugged us too. It bugged us a little bit, because why would I keep a radius and a diameter in the same formula? Because if I look at a circle and I have a diameter can be compared to a radius. So why would I keep a radius and a diameter in the formula? No, I don't like the D. So I'm going to change it to show us that it's two radiuses. I meant to look that up. Radiuses. So it's two of the radiuses, 2r, in the formula. So let me rewrite that. Let's make it a little neater. We've got V equals 2 pi r squared times 2r, all divided by 3. That looks good, right? That looks better. Well, and this is what I did in class yesterday. We said, well, that kind of bugs us too. It's a little messy. There's nothing wrong with it. This whole thing, they all mean the same thing, but it's a little messy. And it's a little messy because 2 times 2 is 4. And all right, so I'm going to have 4 pi r squared times r, all divided by 3. That looks good. Oops, I wrote the pi twice. Does that look good? Does that look good? Well, that was a little messy too. So in class yesterday, we said, well, we can clean that up one more step even. We can clean that up because I can combine some like terms here. So I've got my 4 pi and I've got my 3, but radius times radius, which is radius squared, times radius again, because I have another radius right there, should really be simplified to radius to the third power. Well, that, my friend, looks so much better. That, in fact, is the formula for the volume of a sphere. So we have two ways of writing that. We can write volume is equal to 4/3 pi r cubed, or we can write 4 pi r cubed over 3. So we're going to pick one of those two ways of writing the same formula. My preference is writing it with one fraction rather than writing 4/3 as a separate fraction. I personally like to write my full numerator all over 3 as a denominator. So this is the way I like to write the formula. All right, now we're going to talk about actually putting this into practice. We're going to find the volume of this sphere. So we're going to start with our formula, V equals 4 pi r cubed over 3. And we are going to, like we did before, I personally like to use expanded form. If it's radius to the third power, I'm going to leave myself 3 spaces for my radius. And I'm putting in any values that are constants. 4 is a constant, pi is an irrational constant, 3 is a constant. What I mean is those are the numbers in my formula. Those are all numbers, so I can just move those down. However, r is a variable, and that stands for radius. So I'm going to need, radius. I'm going to need my radius. My radius here is 80, and so I am going to put 80 to the third power, or 80 times 80 times 80. And because I'm using rather large numbers, as soon as I can actually write it out like that, I might simplify it out. I might choose to simplify 80 times 80 times 80 times 4 and divide it by 3. And if I choose to do that, 4 times 80 times 80 times 80, I could use 80 to the third power, of course, divided by 3 is going to give me this value. Don't forget that I had to multiply the whole thing times pi, so I'm going to multiply the whole thing times pi. If you like the pi over here, of course, the commutative property of multiplication tells us that I can put that pi anywhere in there that I want to, as long as I'm multiplying it, I'm going to get that value. And so my value is going to be approximately 2,144,660 and 59 hundredths, rounded to the hundredths place. Now this was centimeters, this was centimeters, this was centimeters. So I am measuring this in centimeters cubed, or cubic centimeters, centimeters to the third power. And that is my approximation. Now, if you wanted to leave it in terms of pi, and you just multiplied that out, you would have gotten, and I'm going to leave this without dividing by 3. If I multiply 4 times 80 to the third power, I would have gotten 2 million. That would be, yes, it is 2 million, just making sure. 2,048,000 pi over 3. That I could have left in terms of pi and then found my approximation. But if we want to round it out, as soon as you can write the formula, you can multiply it all out and you will get the same answer no matter what. I hope this was helpful.